Unfortunately, I'm not part of this development, but I'm very happy is that today we have quantum startups. And so the first talk will be by Haim Suchowski, who is a colleague who, apart from being professor in Tel Aviv University, he starts some real things which we will see if it can give us a real practical advantages. Please.
Okay, it's a pleasure to be here. Thank you, Yaron, for the invitation. Thank you, Lev, for introducing me. Until we'll get the slides. So I'm here from the physics, School of Physics. And I'm going to tell you about, update now. Yeah, that's it. I'm going to tell you about the spin-off for my lab with Professor Aaron Oz and another colleague from the Technion. And hopefully we will have it. Okay, so I'm going to tell you about quantum pulse, it's called Quantum Pulse Ventures, and it's about quantum information processing in the photonic regime. I guess that you heard about quantum computation and a lot of maybe startups. Just yesterday, one of my colleagues from the Weizmann acquired the seed A, $100 million, and there are many ways to do it. So we know that maybe quantum computer will help to something, but the technology, or the technology that will be the one that will implement it, this is the one that we do as scientists, and now part of the quantum revolution. We are part of this revolution to try to find what is the right technology, and maybe all the technology has some place in this domain. This is a little bit an old graph, an old figure from 2021, but it's telling you something about I want you to see. It's taken from this website. This is all the technologies that are known today in order to make a qubit, to realize a real qubit. The main two technologies that sometimes you hear in the news is the superconducting qubit, the Josephson junctions, that IBM and Google, by the way, you see here companies that are part from this revolution, and a lot of money come from the industry, and not just from startups and governments. And each company actually took like a big one, took a direction. So you see here, IBM, Google actually bought the John Martinez lab in Santa Barbara around 12, 13 years ago. Now he's going to win the Prize Nobel this week. But after that, they fired him with an excuse like several years ago. Now he has an own startup, but this is a technology that is one of the pillars. Another technology is this trap ions quantum computers. That IonQ is sometimes you see them in the news when the market goes up, but others, Honeywell, and what you see over here, you see how many qubits, physical qubits they had in 2021. Today they have around 1,000, more or less, this is the number. But physical qubit is something that you really do as a qubit in this technology, but then you need to do the errors you'll see in a minute is not good enough, and you need to make from around thousands of them, you can make one logical qubit that you work with, and in order to solve something useful like doing the RSA, you need thousands of qubits, or sometimes millions, and sometimes billions. It depends how much time you want to spend in order to solve the problems. So we are quite far away. You see here a small company by the name Microsoft. They invested on the wrong technology. By the way, they didn't manage to do it till today. So this is one of them. I'm going to tell you about this technology. This is what we call the dual rail photonic technology. All the rest are what we call material qubits, but this is the only way to do it in photonic regime, and it's inside waveguides, optical waveguides. And there are several companies that are there, Xanadu, Quantum, and etc. By the way, these companies, if you look at them, they also acquired a lot of money. Quantum got around $2.3 billion, 600 million just from the Australian government, and etc., etc. I'm going to move forward. But the challenge, again, in any technology is the error. There are several challenges, scalability, etc., but I'm going to speak about the error because the error of fabrication in all the platforms are more or less above 0.5%. And in order to be good to do what we call the error correction codes, we need to do below a specific threshold, which is around 0.1, 0.2%. So it's above the threshold. This jump is important in order to do a scalable and useful quantum computer. And in this technology, in the waveguide, there is the same problem. And in order to understand the qubit, so 1 and 0, or 1 and 2, whatever, this is the qubits. You can put one photon over here, and then it starts to couple together. And this is what we call the directional coupler. Sometimes I can take them very far away. I need to take them close to do an interaction, let's say an X gate, Adamant gate, whatever, C0, and then I can do with them something. And this is the mathematics. It's a unitary transformation that you can do, you can play. But in order to be accurate, you need this one to be delta beta in the equation here, and it to be very, very accurate. Sometimes it's supposed to be exactly 0, and usually it's not. And the deviation out of it, it's what we call the fidelity of this gate. And usually there is the ideal one that we want, but the one that we fabricate, and if the fidelity is not 1, or what we call the infidelity is not 0, it has an error. And our way of thinking, and this is part of the patent and work that I did 7-8 years ago with 2 talented students, is in order to make these couplers below the threshold. Just to give you just a flavor of this coupler, so if you take this coupler, the coupling between them is something that you can control how much you take them to get close together. If they are far away, the coupling is small. If they are close, so the photon can bump or can jump to or can move and do a superposition easier. But again, everything is based on that these 2 waveguides have to be exactly similar, which after fabrication, they are not. And this is the sensitivity. So this is what you see when it's not coming. So the fidelity is not 1. And if you want to see the errors, so there is only a specific point in this phase space of parameters that they will be okay. But all the rest is not good. It's not good to take this directional coupler, which is something that people already are doing 30 years, to quantum regime. And this is actually the state of the art of all the companies that are using this one. Can we increase the robustness? And I'm going to be very, very short on this one. I have a lecture, usually I'm teaching the audience. But the understanding is how to, instead of taking waveguides and make them uniform, like everybody else does, we understood that if you do some geometrical change, and in the next slide I will tell you what was the thinking behind it, is that if you do some geometrical setting in the right way, but there is a mathematical procedure how to do it, the errors will be reduced up to, we showed up to factor of 6 or something like this, and could even an order of magnitude. And this is something that takes you to the regime of a useful quantum computer. So this is the technology. You'll see this image a lot. Where it came from the understanding that this qubit is actually, has the same mathematical dynamics as other two-level system or other qubits, spins, like you learn maybe in bachelor degree. And actually, the same problem was in the 70s to take these spins and to convert or invert spin up to spin down in a technology that we, back then, the scientific literature was called nuclear magnetic resonance, NMR, but to transfer it to technology, to be an MRI today. The MRI has this flipping and then some decoherences, And the problem was that if you want to do this spin flip, which is taking like the gate that we need, you needed to, it didn't work, the procedure didn't work in spins of a little girl or an old guy, or in Alaska, it didn't work like in the Sahara. So we needed to do something, a scheme that will be robust to this differentiation of errors. And what they invented a scheme that say, sometimes maybe I have some errors, so instead of going directly to the south or to the north, from one state to another, do it in segments. And this is what we called quantum pulse in that rhythm, or composite pulses. And if you do it in segments, you'll be more accurate in the end results. This is the solution, by the way, that we wanted to take. The problem was that in all other solutions that were done in the last 50 years, they didn't take into account the errors inside waveguides, which is a different errors in the term of these parameters. Even though I knew the people that understood how to do it around the world, they didn't move forward to solve the solution. In the end, we had to solve it. And after we solved it in 2016-17, publish it, we understood that it's good for these waveguides. Just to show you, this is the Bloch sphere, this is the qubit dynamics, how it goes. So if you want, this is the target. I don't know if you see it. This is the target that I want to go in this direction, and I have some errors. I know that I have some error. If I take a regular one, I will go to a specific point, which has some errors. But if I will do this complex, again, mathematical procedure that I don't go into the details, 3 segments will take you closer, guaranteed. And the reason is that because unitary time, unitary, it's still unitary. And still it will be on this qubit dynamics. And this is just to show you if everything is okay and this is perfect, so we will have the same fidelity. But if it's not perfect, this one will go reduce very rapidly, and our solution will stay in the regime. And if you really take the numbers and everything was done theoretically, numerically, and in the last 3 years experimentally, we just published paper, and we're still going to publish more papers, going to be there, is that this saving of factor of 3 to 6 is first of all give you the opportunity to be useful for quantum computation. But let's say someone else did something else, maybe better fabrication, this solution will reduce the size dramatically. The size and the time of operation, because you don't need so many qubits, physical qubit, in order to make a logical qubit, and this is another theory. But this is like a multiplication of multiplication, and it can save up to at least order of magnitude of the number of physical elements. And if you hear the news how much a quantum computer will cost and will be in the size, so it's like several football stadiums, and also will be around $1 billion. So if you can save some space, time, and money, this is more or less the hype that the company that we established with the CEO want to take this patented thing. Another thing, in order just to show you one important stuff, in order to say that it's not just a single qubit, in order to show that you are really appropriate to be a quantum information processor or quantum computing algorithm, you need to do also 2 qubit gate. So we went and did a C0, a full quantum experiments. This is something that the company sponsored my lab, and now we have the state-of-the-art lab in Israel to do quantum integrated photonics. The C0 gate, by the way, in photonics is actually 5 couplers. So there are several ways to improve it. Each one of them can be improved, but all the 5 can be improved together. And what you see over here, this is the regular errors that you see. You can see here the errors with the conventional one. But if you take our technology, we reduce the error dramatically. It's actually almost on the edge of the quantum source that we have, or the Ongo-Mandel experiment that tell you how much we have really a quantum light that we measure with. And this is the stuff I see. just to another 2 slides, we are very good for all the technologies in quantum optics, let's say, but specifically to quantum computation to the 2 regime of discrete variable. This is psi-quantums, and also Xanadu, this is a continuous variable, and also, just to show you, maybe there is an image, what the thing is that you don't need to change your philosophy of how to build a quantum computer, just change this transistor and change it to something that will be more accurate, and you will save a lot. This is Ofer, leading the company. We are the professors that support this one. Until now, we were very needed because we needed to really show things. So myself, Yaron, and Moti, the board director. So again, this is the thing. It's a robust coupler, low physical errors. It's 100,000 elements instead of 1 billion. It's an order of magnitude in the size. And just to show you that we really went out of the stealth 2 months ago, even 1.5 months ago. So this is the American Yahoo Finance stuff that if you want to read, you can go there. And more importantly, to be published in Ynet in the 1st of December. So this is even important because then your mother and father can congratulate you. So this is my stuff.